Hello everyone, thanks for watching this video. Today I will be talking about a deterministic near-linear time approximation scheme for geometric transportation problem. The work is done by me and my PhD advisor Emily Fox. First, let's introduce the problem in definition briefly. Suppose we are given a point set P and a supply function mu mapping each point to a real number such that the total supply value of all points equal to 0. Then we say a transportation map Tor is a non-negative assignment to every pair of points such that the total assignment leaving a point is equal to its supply value. This figure shows an example transportation map where the dart and the blue number associated with the dart shows the assignment value for the pair of two endpoints of darts. So the problem is to find an optimal map that minimizes the cost of the map with respect to the Euclidean distance. Let the cost of P mu be the minimum cost. Then we call this cost the transportation distance, which is also known as the Earth mover's distance if we consider the problem as we are given some piles of earth and some holes, and we are asked to find a way to move all earth from piles to holes and minimize the total earth miles we use. This problem is known to be polynomial times solvable by converting into a minimum cost flow problem in a bipartite graph. Okay, for the known results, Orlin's strongly polynomial time algorithm can be used to solve the bipartite graph mean cost flow in near cubic time. In 2017, Agawa et al. Developed an exact algorithm for the problem when the input is in 2 dimensions. In 2019, Cassin et al. Gave the first near-linear time approximation scheme for the problem assuming the total supply value is polynomial small. 1 year after, Fox and Liu improved the result by removing the dependency on the input value. However, to the best of our knowledge, no subquadratic time deterministic 1 plus epsilon approximation algorithm has been developed for this problem. Also, I want to emphasize that there is a deterministic almost linear time general mean cost flow algorithm, assuming bounded integer supply values, appeared earlier in this conference too. That algorithm can be used in the second step of our algorithm to generate an almost linear time deterministic algorithm for the problem. But from now, we will just focus on our strongly near-linear time approach. Our algorithm is strongly motivated by the recent result for spatial case of the transportation problem. The geometric bipartite matching. Agawa et al. Described the first near-linear time deterministic approximation scheme for the problem in Stock 2022. That problem is a special case of the transportation problem where you have unit supplies and the assignment are all integers. Okay, their problem actually is the first deterministic near-linear time approximation algorithm for the special case where the randomized algorithm for the same problem was developed 10 years ago. This shows the difficulty of the de-randomization. Okay. We show that there is an algorithm that runs in near-linear time if both epsilon and dimension are constant, and guaranteed to retain the transportation map with cost at most 1 plus epsilon factor of optimal. Note that the polylog part in our running time does not have dependency on D. This is not true in the deterministic bipattern matching algorithm, and also not true in any previous transportation approximation scheme, the randomized or deterministic. In high level, we first build a spanner which can approximate the pairwise Euclidean distance of P deterministically, and reduce the transportation map problem to a mean cost flow instance in this spanner. Then, we compute an approximation for this mean cost flow in near linear time. Finally, we recover a transportation map from this approximate flow on the spanner. Okay. So first, we build our spanner based on the conditional compressed chord tree introduced by Fox and Liu and the tree cover idea in this deterministic geometric bipattern matching algorithm. This spanner is built through the net points, or the standard vertices we added to every non-empty cell of the chord tree. Besides the edges we added to connect the net points of every cell to the net point of their parent cell in the chord tree, we also directly connect every net point to all neighboring net points of cells that are at most 1/2 epsilon grid cells away from C. We use this like a slide to show how it works. For example, this figure shows that a cell and its 4 child cells in 2 dimensions, of course. The net points of its child cells are connected to with its own net point. Moreover, for every net point nu, we're directly connected to all its neighboring net points that are at most 1/2 epsilon grid cells away. This is very important to achieve this deterministic approximation ratio of the spanner. Okay. We also add edges from every point in the original point set P to the net point of the leaf cell containing it. Then we can show for every pair of points in P, the lowest level at where the ancestor point in the spanner are directly connected will have cell size at most O of epsilon factor of their Euclidean distance. By triangle inequality, the spanner's 1 plus O epsilon approximation ratio can be derived easily. So this slide shows how the distance is approximated throughout spanner. So this is a pair of points. Then we build the spanner and through the chord tree, and connect the 2 points through the net points. Okay, now we have the spanner ready, and we are also ready to reduce the problem to a mean cost flow problem in the spanner and solve it approximately. Here we will apply Sherman's generalized preconditioning framework following the previous randomized results did. We formulated the mean cost flow instance in the spanner as finding a mean cost flow F such that AF equal to B, where A is a vertex edge instance matrix of G, and the B is a divergence assignment, where B of P equal to the supply value for every P in the original point set, and a B of V is equal to 0 for every vertex V added to the spanner. In short, we want to find a preconditional B with the small condition number kappa satisfy this following inequality. Note that the optimum value of the mean cost flow instance will be at most 1 plus O of epsilon factor of the transportation distance by the spanner's approximation ratio we mentioned earlier. Okay, the big challenge for our algorithm is indeed in the step to compute the mean cost flow. How to find a good preconditioner with small enough condition number? for example, O of log n. All previous results are able to describe a simple greedy approximation algorithm that repeatedly pushes flow from net points to their parents. And a preconditioner can be built by simulating this writing algorithm easily. Because in the spanner of previous results, the only way for a surplus leave a cell is to go from its net point to its parent, along the core tree. However, now close by pair points may have a distant ancestor in our spanner because we might connect two net points that are much more far away than their own cell size, because we need it to achieve this deterministic approximation ratio spanner. The same preconditional construction method may now result in a condition number polynomial in the spread of P. Note here, we focus is the polynomial in the spread of P, not even the log of the spread. Imagine that the algorithm keeps writing flow through the paths further away from the optimum path between 2 points. But luckily, we find another greedy algorithm to approximate this mean cost flow that is good enough and also straightforward enough so it can also be used to build a preconditioner. See, our core tree construction is deterministic, but we will pretend it's not. So for every vertex U and for every cell that are closer to the root of the tree than this vertex U, we compute the probability that a random shift of the core tree will cause this cell C to continue U. Then our algorithm will write an equal portion of U's surplus to the net point of C. Now, suppose a mean cost flow sends some flow from U to another vertex V. Then, for every cell C that gets non-zero surplus from either U or V, the proportional difference of surplus it gets from U and V will be at most the minimum distance along any dimension over the shifting space. And of course, it cannot be bigger than 100%. This slide shows how this random shifting is simulated. Imagine that we are shifting the grid along the diagonal. Then for every point, there are at most D plus 1 cells will be able to contain the point when the shifting space is equal to the cell size. The distance between 2 points U and V is fixed, because the cell size keeps increasing when we move closer to the root. So the total supplies from U and V that does not cancel out will also decrease by equal factor every time when the cell size increases. The largest distance between any pair of ancestors of U and V is increased again by the same factor 2. Together, they imply that the approximation ratio of our greedy writing algorithm is proportional to the height of the core tree, which is log of spread of P when the spread is bounded. In the case of unbounded spread, we can actually afford to slightly move the axis-aligned hyperplanes bounding the cells so that no input point will lie in the forbidden region from any cell boundary. This padding is referred to as modes around the points by Agua et al. With this, we are able to force any pair of points U and V to be in the same cell when the cell size is large enough. For example, when the side length of the cell is at least n square factor 2 of their Euclidean distance. This will bound the approximation ratio of our writing algorithm to O of log n. Now a preconditional B with condition number O of log n can be then built through setting every entry of B of U and V to a value proportional to the portion of with supplies we route from V to U in our greedy routing algorithm. That plus some dynamic programming method for evaluating the application of BA and BA transpose implies that we can compute a 1 plus epsilon factor approximation of the mean cost flow in near linear time using the preconditional framework. Okay. But we are not done yet. We need to find a transportation map from this flow. Because this recovery method in previous results will all rely on the spanner has a particular structure. Again, thanks to the complexity of our deterministic spanner, we can no longer use this recovery method. So we need to invent a new way to compute the transportation map out of the spanner's flow. Indeed, our new method is a general scheme that can be applied to any flow on a spanner over B, with or without standard vertices in near linear time. Okay, we show there is a simplification of our algorithm for low spread case. Recall that in low spread case, we do not need modes, and we can just use the standard chord tree given the bounded height of the chord tree, which implies a simple and faster version of our algorithm. Because approximating the optimal bipartite matching can be reduced in n log squared n time to an instance where the spread is polynomial in n. Therefore, this simplified version of our algorithm can be then used to approximate the geometric bipartite matching problem in near linear time. Note, this also relies on the fact that our recovery method will produce the integer flow assignment if all supply values are integers. Another application of our algorithm is to approximate the incapacitated mean cost flow in general graphs. And don't at all show how to do this in general graphs with integer edge weights by building preconditioners for the geometric transportation problem. By applying our deterministic preconditional construction for transportation, we also show that there exists a randomized algorithm that runs in time m epsilon to the power of -2 polylog n time, and retains a 1 plus epsilon approximation with high probability for arbitrary edge weights. And that's all for my presentation. Thank you.